Okay, welcome back, everybody. Moving on to part 3 of the book and the semester. So feel pretty proud of yourselves. You're 2/3 done. Part 3 can be a little bit more broad in its application. Certainly for numerical methods, you can imagine that. In reality, this is what most engineers, physicists, everybody who's doing PDEs actually uses to solve problems, because the total number of PDEs we can solve are quite small in any sort of closed form. And then spectral methods are actually incredibly important. They're actually kind of related to numerical methods, but we'll try to develop them first. Spectral methods are really a way of describing properties of solutions or interpreting PDEs in the perspective of linear algebra. Anytime somebody refers to spectral methods, they're usually saying, okay, how can we apply some sort of a linear algebraic lens to PDEs problems? And certainly, this is how it relates to numeric, is if I can reduce a PDE to a linear algebra problem, then computers can invert my matrix to solve the system. So spectral methods, anytime they get applied, anytime somebody refers to spectral methods, they're really saying linear algebra methods, perhaps in infinite dimensions, in which case it's kind of functional analysis instead of linear algebra. But they're basically saying, how can we apply the tools of linear algebra to really any sort of mathematical problem? I mean, spectral graph theory is a thing, and that's not really related to PDEs at all. So spectral more or less means, hey, we're sending ourselves into linear algebra. We're going to tackle that first. But secondarily, every time, you have a relationship with linear algebra, all of a sudden you have a relationship with numerics, because numerical linear algebra is probably currently the best tool that mathematicians, applied mathematicians, physicists, engineers, etc. have, period. Numerical linear algebra on computers is by far the most powerful applicable tool that mathematics has given us in the real world. So spectral just means converting things into linear algebra. Numerical, obviously, we're going to be actually performing some approximations. So that's what this part 3 is going to be about. So you should feel really excited. This is kind of the meat and bones of the applications of PDEs, even though the meat and bones of the PDEs themselves were the first 2 sections of the book. So this very last part of the book is the applications, but the first 2 were really kind of digesting PDEs as a whole. Anyway, we're moving on to chapter 5. It's called Green's functions and spectral methods. Once again, we see this word spectral show up again. You probably see it a lot. Green's functions are kind of a specific approach to these spectral methods, and a very useful one. We're going to start with section 5.1 called integral transforms. So we're really looking at kind of a broader picture of our Laplace transform from ODEs, or our Fourier transform from this semester, and trying to generalize this as much as we can. So let's just take a look at the Laplace transform again. This is kind of throwback to some ODEs here. So the Laplace transform was an integral from 0 to infinity of whatever function we were looking to transform. And then we multiplied that function by e to the minus st and integrated over all of time. So the important thing is that since we're integrating over time, t, that's going to 0 to infinity, the output here is some function, I'll give it the name capital Y, of the very last variable here, which was the variable s. And so we're going to start to see this kind of show up as integral transforms are cases where we have integrals where 2 variables are sitting around, and one of the 2 gets integrated over. And in fact, the one that gets integrated over always has to be the variable in the function that we're actually trying to transform as well. So you integrate over one variable, and another will necessarily be left behind. So the one that's left behind is, the variable of the new function that you recover. So that's going to be a commonality here. And looking at our Fourier transform that we encountered in part 1 of this book, and then we basically never left it because it's one of the most useful tools we have in PDEs. The Fourier transform, at least in one spatial dimension, we would integrate from minus infinity to plus infinity, take our function of x, and then we multiply that by e to the imaginary, right, e to the negative I xy. Then we'd integrate against x, and there's this normalization out front that really isn't terribly important, but once again, I want to cover that the variable x, which was sitting inside of the function that we're trying to transform, variable x here, also occurs in the exponential, and then it's the variable that gets integrated over. And what we're left with is a y here. We're left with some phi hat function of whatever variable is left over. And so this is kind of the commonality between these 2 transforms that I've introduced so far. And in fact, both of them were associated to convolutions. We probably covered this a lot more in ODEs than we have in this course, but the convolution described by the star between two functions is an integral. In the Laplace transform setting, the upper bound of the integral is a variable itself. In the Fourier transform, it's not, but we take our one function f as a variable of s, and then another function g, which is actually a function of two variables, t and s, and then we integrate over the variable s. So we're integrating out the variables s, so they're all gone, and we're left over with some function of t. And then once again, in the Fourier setting, there's a convolution as well, and it's got its normalization up front, the integral over r, now f of y, g of x minus y dy, and so we're integrating over the variable y here, and what is left over is a function of the last variable, x. And so this is just a commonality of all sorts of things we've kind of experienced already, but I'm trying to hint at a motivation for kind of developing this next definition, kind of the generic definition that encompassed everything that we've seen so far. This is called the integral transform. The integral transform is actually a linear operator, okay, because it's going to, anytime mathematicians refer to operators, what we're actually referring to is a map from one function space to another function space. Okay, so it's a map that takes in a function and outputs a function, rather than functions which take in numbers and output numbers. Operators are going to take in functions and output functions. So the derivative is an operator, for example. You plug a function in to a derivative, you get a function out, and it's not the same as the function you got in a lot of cases. So it is going to be a linear operator, and it gets a representation as an integral. That's what it means to be an integral transform. In fact, its representation is an integral over the function's domain, right? This is omega there, and we're integrating in the y variable of the function that I care about. So it's an integral over the function's domain against, right? So the funny thing is that it's always an integral against something else, against another function of two variables. And of course, those variables can be vector valued. So they don't have to actually just be like two one-dimensional variables. They could be two 45-dimensional variables for all I care. But it's a function of two variables, one of which is the same as is integrated over. Hence, we are left with a function of the remaining variable. So this k here will always be a function of two variables. It also sits inside of the integral. One of those two variables, y here, is the variable we are integrating over. The second variable, x in this case, is left around, and that is now considered the new variable of the output. So this function k is called the kernel. It just has to be a function with two inputs. That's what this omega cross omega star means, two different inputs, where omega is, of course, the one that we're integrating over, and omega star is whatever x decides to sit inside of. In some cases, it could be the same as omega. In other cases, it could be something new. It could be a new set that our new variable is evolving over. So that's just a function of two variables, and it's called the kernel of this integral operator L. So a lot of times we'll refer to kernels. You shouldn't think about, this is a very frustrating piece of mathematics, is that this word kernel of L has nothing to do with the null space of the operator L. Recall in linear algebra, one could refer to the null space of a matrix as the kernel of a matrix. So it's a little bit frustrating that we have this word kernel of a linear operator. It's not related to the null space at all. It's just a name that we give. So fortunately we have these homophones. So the same name for two different things. And we just have to be aware that when we're dealing with integral transforms, we're not referring to the null space as the kernel. We're referring to the function inside of the integral transform as the kernel. But you do have to use your context clues to figure that out. Sometimes a lot of mathematicians will get you confused because they'll say kernel and you have no idea what they're referring to. Anyway, with that said, let's look at some examples. of these integral transforms, and we actually did already see 4 of these examples, but let's make it explicit in these example boxes by actually defining our kernels with what they should be. So if I define the kernel, k of t and s as e to the minus st, what do you know? That's exactly the Laplace transform. If I reconstruct a kernel transform, or an integral transform, with that specific kernel over a specific domain, which has to be 0 to infinity, and a specific related domain, right? This is the domain of the image as all of R. This is the Laplace transform. So the integral transform defined by that kernel, that domain, and that we technically call this second domain like the dual space sometimes. The Pontryagin dual is sometimes how you refer to it, but whatever you want to call omega star, you can call omega star. The image domain, perhaps. But that'll be the Laplace transform. The Fourier series transform is also an example of one of these. So earlier I just introduced the regular Fourier transform, but the Fourier series transform is also an integral transform in the event that k, our kernel, is a function of x, the real valued space, as well as n, just the integers, right? So if we take omega to be kind of our interval, negative pi to pi, but omega star to be z, the integers, then we still actually have an integral transform, because what happens when I do 1 over 2 pi e to the minus I n x and I integrate over my space, some function over that space, that's exactly the Fourier series transform. And of course you saw the Fourier transform earlier, but we also will cover it now. The Fourier transform is an integral transform. Now omega has been changed from just an interval all the way to R, and omega star is also R. And our kernel is going to be 1 over root 2 pi e to the minus I y x. And if we set up this integral transform, we see it's exactly the Fourier transform we've been used to our whole lives. Then we can talk about convolutions. In the Laplace convolution, which I introduced at the beginning, we do have to be a little bit careful on the kernel here. Not only is it whatever function g that we're trying to convolve against, but there's actually a Heaviside step function here. The unit step function, perhaps, is the way you saw it in ODE. Sometimes this is notated with a u, or even a script u for the unit step function. And so if you multiply those two together, that's actually your kernel, because if you integrate over the Laplace setting, which is the positive real line, you look at this kernel, because of the unit step function's properties, it cuts off the real line at t, and then you're just left with g of t minus f times f of s ds. So this is exactly the Laplace convolution. And then Fourier convolution is even easier than that. We just have 1 over root 2 pi times g of x minus y for our function of both y and x. Plug that in and we see exactly the Fourier convolution. So all sorts of great examples of integral kernels and transforms. You can go onto Wikipedia or other online websites and just type in integral transform. You'll see a table of maybe 50 of these that are actually quite relevant to mathematics. So you just want to think about, you really put whatever you want here for k, and the operator that results will have some useful properties in a lot of situations. So really, the whole point of this chapter in the book will be right here. This is the point of the chapter, and by this is the point, I mean finding useful k's is the point. So finding useful k of x, y is the point of the chapter. So that's what we can be thinking. Let's look at some non-trivial examples. You've been computing integral transforms implicitly for a while now, because you've been computing the Laplace transform and the Fourier transform. So you're very used to computing these things. But let's just do it with an arbitrary choice. So here I am. I just showed up and decided, hey, I'm going to define k of yx to be sine of x times cosine y. I'm defining omega and omega star to be the interval 0 to 2 pi. And what the heck, let's transform the function cosine x. So what is the transform of the function cosine x when my kernel is sine x cos y and my space, my domain, is 0 to 2 pi? We just plug everything in. At this stage, by its definition, omega is 0 to 2 pi. K of yx is sine x cos y. And then this is a little bit important. Notice it's an f of y here, so I do have to replace the variable there. That was f of x. So I do have to replace that variable of cosine x to now cosine of y. But when I do that, all I have to do is find my integral here and compute. It's not too bad to compute, because if I'm integrating the variable y, the sine x doesn't care, so I can pull the sine x up front, and I'm left with the integral of cosine squared y from 0 to 2 pi. For those of you who don't quite remember from Calculus 2, I wouldn't expect you to. This is where we use technically the double angle identity of cosine to convert cosine squared into a 1/2 and then a 1/2 cosine 2y, where you can integrate 1/2 cosine 2y using u substitution as 1/4 sine 2y. So you just integrate those, you get the following evaluated bounds, and you find out that this term is exactly pi. So you end up with pi sine x. That's what the transform of cosine x under the integral transform defined by that kernel happens to be. You do the same thing with a new kernel. Let's do it with the kernel 1 over x squared plus y squared. Let's say our function is 2x plus 1, and let's say that our domain and dual domain is 0, 1, the interval. All I do once again is write out the definition, replace omega with its actual bounds, replace k with its definition, replace f of y with its definition, and then it's time to compute. In this case, our life is not quite as easy because we don't have a multiplicative function of x. It's now in the denominator. So we can't just pull the function of x out front. We're just going to have to compute this integral as is. Now, when I'm computing this integral, I immediately see that this term looks like a chain rule. If we're integrating in dy, it looked like a chain rule in the forward direction, which is also known as u substitution in the reverse direction. And then I'm also noticing that this looks a lot like the integral of arctangent, or the derivative of arctangent. So I'm going to split up my integral, add the plus sign in the numerator to just do 2y over x squared plus y squared, and then 1 over x squared plus y squared. And if I integrate this with u substitution, I just get the log of the denominator. If I integrate this with u substitution, I get 1 over x arctan y over x. And then I'm going to evaluate these at my bounds of 0 and 1. If I use logarithm rules, I can simplify the logarithm once I've evaluated at 1 and 0 to log of 1 plus 1 over x squared. And then the arctan, just recall arctan at 0 is 0, so that's why that term no longer showed up. Now keep in mind, because this is a y, dy, dy, 0 and 1, when I write the 0 and 1 here, make sure that you know this is in the variable y, that's getting plugged in. So not the variable x. The variable x sits along for the ride. Just look back at your integral to make sure that you're plugging in those values correctly. So there we've seen just a huge collection of these integral transforms, and what I'm actually going to do now is I'm going to change gears because, yeah, the Fourier transform, the Laplace transform, convolutions are useful mathematical objects, but I'd like to motivate this the way that it really probably should be motivated. It shouldn't be motivated just as, hey, we've discovered Fourier and Laplace transforms. They were useful. Let's see if other ones are useful. It's actually stronger than that. We can actually motivate this really well with the following proposition. Proposition says integral transforms describe infinite dimensional matrix multiplication. What the heck does that mean? Infinite dimensions. Well, we kind of talked about it a little bit with our Taylor and Fourier series. Those are infinite dimensional objects. Well, really all functions are. But more or less, we're going to talk about how matrix multiplication, which just looks like taking a matrix and multiplying it against a vector, is in fact the same operation as an integral transform. They look completely different. They look like not even close to the same operation. But let's just zoom in really quick on the fact that every m here in my matrix is defined by 2 coordinates, right? The matrix entries are defined by 2 coordinates, and vector entries are defined by 1 coordinate. And what happens when I actually perform the multiplication is I take all of my vector entries, I rotate my vector against the matrix, and I multiply it by every row of the matrix. So, and then you sum, right? You're going to do the inner product of those two, the row of the matrix with the column of the vector. And so we perform a multiplication of a vector against a row. That's very important. That's just a row of the matrix. And subsequently sum across. I'm going to underline a couple words here. Multiplication of a vector against a row, and then we sum. Now what I'm going to do is jump over to the integral transform here, and let's see what we do. We take a multiplication of a vector, because a vector is defined by 1 coordinate. So which one is defined by 1 coordinate here? It's a function. The function is defined by its variable. It's 1 variable. You take a multiplication of the vector by the matrix, but it's just a row of the matrix. Where is the row showing up here? Well, it's showing up in the fact that y is the only one that's being summed over. So only one of the 2 indices. This is the row, I'll put that in quotes, of the matrix. So the fact that we're only summing over one of the two indices of the kernel, and then we sum across, but our infinite version of a sum is an integral, this is exactly the same sort of operation. I'm actually going to go through the proof now. The proof may make it a little bit clearer as to why this is working out for us. Let's look at the definition just using summation of matrix multiplication. So if I define my matrix indexed by two variables like this, and my vector indexed by one variable, you can actually define the matrix vector multiplication as the sum over, m sub 1j vj over all j's, and then m sub 2j vj over all j's, and m sub dj vj over all j's. So that's an alternate way of defining matrix vector multiplication. But I can make my life even crazier by condensing the notation again and just saying, hey, let's look at every row one at a time of the matrix vector, and then it just looks like this sum, the sum from 1 to d in the j variable of mij on vj, and then the I sits along for the ride. The I is now my new variable in some sense, right? So I is the new variable, or I'll say resulting variable of matrix vector product. Maybe to make my life a little bit clearer, I'm going to say, well, instead of using subscripts as indexes, I'm going to use function notation as indexes. And instead of a subscript there, I'm just going to write, hey, that's a function of I, which means that the matrix entries are functions of I and j, and the vector entries are functions of I. And then the matrix multiplication is a sum of a function of two variables against a function of one variable. And one of those two variables, right, the variable that shows up in both of them, is summed over. That's exactly what matrix multiplication looks like. You could extend this to infinitely many dimensions if you wanted to. You wouldn't have to restrict yourself to a d there. You could go all the way to infinity if you want to, and everything is perfectly well defined. You may not be able to represent your matrix the way that you would be used to it, but it's well defined. And what can we actually do if we're thinking about this in terms of functions of variables? Is we can say, hey, how about the indexing on my matrix I, this term I on my matrix, let's actually just divide it by the total length of the matrix and make it I over d. Then what do I have? Is my matrix is indexed by 1 over d, 2 over d, all the way to d over d, and that, as d grows, is a partition of the interval 0, 1. Let's write my interval over here so we have an idea of what we see. Let's make this the real interval. If I index right here at 1, would that be about 1/10, 2/10, 3/10, 4/10, 5/10, 6/10, 7/10, 8/10, 9/10, and 10/10, you could represent the matrix as taking values at each of these 10 points if you want to. You don't have to, but it's one way of thinking about the matrix. Fine, let's have the matrix take values at those points, and the vector take values at those points. And then let's let d go to infinity. When we let d go to infinity, we're now letting the matrix and the vector take value at infinitely many points here, in between 0 and 1. And what is that? That's a function. A vector taking a value at infinitely many points is just a function. And so we can replace v here with an f. We can replace m here with a k. So I'm going to show this in images now with a specific set of k's and f. Okay, so let's do an integral transform. I'm just choosing a random k out of the box. Let's do the integral transform where my kernel is x minus y cosine 2 pi x times cosine pi y. And let's decide that f is sine of 2 pi x. Okay, so then at the end of the day, what are we actually computing if we compute the integral transform? There it is. This is just k times f integrated from 0 to 1, and this is the result. We can see what that looks like. This is f of x over here. This is L of f of x, the integral transform. Perfectly well defined in terms of functions. Everybody probably can actually compute this antiderivative if they want to, but I want to send ourselves back to really thinking about these as the limit of vectors and matrices with infinitely many entries. So let's go ahead. I'm actually going to skip ahead of that, and let's go ahead here and let's discretize our interval 0, 1 to 10 intervals. And when we discretize this sine function, sine of 2 pi, over those 10 intervals, it just takes its 10 values, shown on the left, and then our image here of LF also takes 10 values. And these are both can be represented by vectors, right? So I could represent this as a vector. If this is like 0, 0.6, 1, 1.6, 0, negative 0.6, negative 1, negative 1, negative 0.6, that is a perfectly well-defined vector. You just write it out. 0, 0.6, 1, 1, 0.6, 0, negative 0.6, negative 1, negative 1, and negative 0.6. That is a 100% well-defined vector. And you could develop a matrix, M, some big matrix in here, for which if I multiply that matrix times this vector, what do I get? I get whatever's on the right here, which is like negative 0.2, negative 0.15, negative 0.1, 0.1, 0.1, dot, 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 right? So it could give out this image of negative 0.2, negative 0.15, dot, 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 and finish that image there. You could definitely come up with that matrix. Well, how could we come up with that matrix? It's not that hard. It's really not that hard. All we do is we calculate the discrete version of this, evaluate it at each of those discrete intervals in space. Here they are, right? And then you just plug those into K, and you get yourself a nice big matrix whose values are all the correct values you would want, so that you can map this into the correct image. Now, let's think about what actually happens in both the continuous case of the integral and the discrete case of the matrix. In the continuous case of the integral, what's actually happening when I compute this integral right here? Visually, what's happening is I'm taking my input function f, the sine, I'm taking it, and since I'm only making it a function in the y variable, that's my y direction. So I'm going to place it in the y variable. I've got my surface. This whole surface is k. The surface is k of y comma x, and I multiply them together. So I'm multiplying sine against k of y x, and then I integrate along the line that I've multiplied them together. And what I've shown here is I've shown the output of that integral at one specific place. Then as x evolves, there's my x direction here. As x evolves, I'm just moving the sine function to the right, and at every step along the way, I'm computing the integral along that multiplication, and I'm going to plot it here. This is me plotting what the integral is actually equal to on the output there. And what do you know that function is on the output? This function on the output right here that I've plotted is exactly this function right here. It's exactly the true image. And so we can think about the integral transform as a rotation of f against k, then integrated along their overlap. And this is true for each x. So you just rotate it against your surface and integrate along that, and the output for every single x, you get your image. But that's exactly what happens with matrices on vectors, right? So what I've done here is I've taken k and I've discretized it, as I mentioned earlier. And this is actually a representation of a matrix. I don't know if anybody's ever thought about a matrix this way, but because a matrix has a value, right here, maybe the matrix has the value 1, maybe it's got value 0.8, 0.4, negative 0.1, negative 0.3, whatever, right? You can think about a matrix, you could graph it graphically as whatever values are in the matrix is just the height of a surface. And this looks a little bit like Minecraft right now, right? Whereas if you zoom really far out from a Minecraft surface, field, whatever you want it to be, mountain, then it looks visually almost correct. It looks almost like a true surface. So this would be the idea: as you make higher and higher dimensions in your matrix, you get closer and closer to the true surface by discretizing. But you can just think about it in the case of a 10 by 10 matrix. What's happening when we compute the matrix vector multiplication is we have our discrete vector here. Here's the vector, which is the discretized version of our sine wave. And if I take this vector and I perform matrix multiplication of my matrix on that vector, what happens? I rotate the vector against the matrix, multiply them together, and sum the output. That is matrix vector multiplication. It's a multiplication of a rotated vector against the matrix, and I sum the output. There's me summing the output the same way I did before, and what we get is an approximation to our answer. Right? That's where we get this approximation to the true answer. So that's really all I want to stress is these integral kernels are just infinite dimensional matrix multiplication. You can read through that proof. I think I did a pretty good job writing it out. But that's where we're going to stop today because I know it's been a while, and we're going to cover the rest of the section in the next class. See you then. Bye.